Supernova Week continues here at Trekzone today. Talking Science interviews. I'm going to jump back in Studio 4 after the opener. Chat with James Painter. He's a PhD student down at the University of Melbourne, and he was looking through old data, decades old data in fact, and found a intermediate mass black hole. This is a very exciting discovery. He's going to tell us why on this Talking Science interview as Supernova Week continues.
Beaming around the world on Apple Podcasts, Spotify, Google Podcasts, and YouTube. This is Talking Science.
And James, thanks for a little bit of your time on today's Talking Science interview. I really appreciate it.
Thanks for having me on the show.
Now, can you tell us a little bit about your research? You've discovered this Goldilocks black hole. First of all, what's a Goldilocks black hole?
I think the technical term actually is an intermediate mass black hole, and the name Goldilocks came about because it's not too big and not too small. So, there's two very well-known populations of black holes: the supermassive black holes, which lurk in the cores of every galaxy, and then there's stellar black holes, which come about as a result of supernova explosions at the end of a star's life. And these are about 10 times the mass of the sun, 50 times the mass of the sun. And the supermassive black holes are millions and millions to billions and billions of times the mass of the sun. But this intermediate mass range in between is so far a very unexplored region of the parameter space. And so I think that's where the name Goldilocks came about, because it's not at the smaller end and it's not at the bigger end, but somewhere right in the middle, somewhere just right, if you will.
And it is a crucial link, as you say, not quite as well researched as, say, the supermassive black holes. Trying to find that missing link on how the black holes become supermassive and get to become the size that they are is crucial. And finding these intermediate mass black holes is very important. What else can we learn from them?
I guess the well, one of the most exciting things here is that we don't quite understand how the supermassive black holes form. If they form from a supernova explosion from a star right in the very beginning of the universe, and they accreted mass at the maximum rate possible, within a few 100 million years, there's not enough time for them to grow to be 1 billion times the mass of the sun. But when we go out and we look into the universe, we can see objects in the very, very early phases of the universe, which are 1 billion times the mass of the sun. So we have to think, well, what could possibly be seeding these monsters that are out there? And so the most exciting channel is that perhaps it's an intermediate mass black hole, and perhaps there's a whole population of these objects in the universe which are out there, which are so far evading most observations.
Now, this black hole was discovered through a gravitationally lensed gamma ray burst. What exactly is that, James?
Yeah, it's a bit to unpack there. So a gamma ray burst is a flash of X-rays or gamma rays that signifies the birth of a stellar mass black hole. So it's either in a supernova explosion at the end of a star's life or during the merger of two neutron stars. You've got this flash of X-rays that we observe. And now this is happening very, very early in the universe as well. And on the odd chance that there's something between us observing it here on Earth and then some distant object, that gamma ray burst, if there's something just sitting perfectly along that line of sight, what happens is the gravity of that object will start bending and distorting the light of the background source. And so we call that gravitational lensing, because it's acting like a lens due to its gravitational field. And so in certain scenarios, you actually can have multiple images where the light has gone either above or below the lens and been bent back towards the observer by the gravitational field. So you can see multiple images. So what we've detected is a gamma ray burst, which has been gravitationally lensed, and we've seen this multiple imaging of that source.
So, James, this black hole is very interesting in that it's a primordial black hole.
It could be. So we don't actually know we don't actually know the exact formation channel of this black hole, and because our detection method is through a gravitational lens gamma ray burst, we don't actually have a lot of extra information about this black hole. So it could very well be primordial, or it could have formed through the rapid merger of a cluster of stellar black holes very, very early in the universe, from the very, very first stars. So a lot of these stars go supernova, they're already in a cluster, and then they will rapidly merge with each other. That's one possible scenario. And then another, as you said, is it could be primordial, formed in the very first moments after the Big Bang. But we don't know for sure. And I think now that these objects are being discovered more regularly, there's a great opportunity for theorists to come up with more accurate theories for exactly how these objects might come about.
And what's it like to have the discovery confirmed of a black hole? You've seen it there, the gravitational lensing that we talked about, and to have all that confirmed, and yes, it is one of these Goldilocks black holes. Must be very exciting, and I guess now the research continues. You know where to find it, and you can keep looking at it.
Well, this particular event happened way back in 1995. So, as I said earlier, there's actually not that much extra information available for us to go and look at this object in more detail. And due to the way that gamma rays are detected, so they're very, very high energy light particles, they can't be focused like you can focus light in a telescope. So we can't get beautiful images like you see from Hubble. We actually just have very high time resolution, but the spatial resolution is terrible, much larger than the pixel size is much larger than the sun or the moon on the sky, for example. So we can't really zoom in on this object and discover more about it. But what we can do is find more objects from this population. So we can look through all the other gamma ray bursts and even fast radio bursts and other transient population of sources, and see if we can find more lensing effects. And that would tell us that there is more of these objects out there, and we can better determine how many of them there are in the universe and what their distribution may be.
And this is one thing that I think is really fascinating, that we get to not only new observations, but also past observations. As you say, this discovery was made a couple of decades ago now, but we can pull back over research. There's so much information being recorded from our night skies, or our skies in general, that there is so much to discover. I guess what's that sort of like to know that there's a wealth of research out there as well that we can pore over and see if we can find more of these black holes.
I guess it's an exciting opportunity. I mean, the data's there, so I don't have to do any work, or whoever's looking doesn't have to do any work. All the hard yards have already been done, and we just have to go and sift through it and analyze it and try and uncover these things. But the hard work of building a telescope, launching it into space, doing all these calibration checks, that's already been done for many different iterations of gamma ray burst satellites. So yeah, I guess it feels good to be able to do great science while at the same time sitting back and relaxing and not having to put in all the hardest parts of the work to get it off the ground.
I love it, James. Thanks for a little bit of your time on Talkin' Science interviews. Congratulations on the find. Looking forward to more discoveries coming from you. Hopefully another one in the not too distant future.
Thank you very much. I'm looking forward to that too. Thanks for having me on the show.
Keep up to date with Twitter. Catch new podcasts daily on YouTube. Plus, we're beaming to your favorite podcast app 5 days a week. Just search for Trekzone and subscribe.